In this lesson, we shall do mathematics, maths, probability, grades 11 and 12. We shall focus on Venn diagrams. We shall also do mutually exclusive and inclusive events. We shall also do independent events and so on and so forth. We shall cover as well tree diagrams, past examination questions, and a lot of parts that are covered in the curriculum under the section or chapter on probability theory. And we continue as follows. Right, first things first, we shall look at question 4. And question 4 is on probability. Right, and in question 4, we are so now our approach is going to be using past exam questions and past assessments to actually try and understand what you need to know. Through the discussion of past exam questions, it is our hope that you will actually be in a position to have the skills cultivated that will enable you to succeed in the oncoming assessments. Right, the events A, B, and C are such. A and B are independent. So we are told that we have two events, A and B, that are independent. Simultaneously, B and C are independent. A and C are mutually exclusive. Right, their probabilities are as follows. The probability of A is 0,3. The probability of B, 0,4. The probability of C, 0,2. Calculate the probability of the following events occurring. Right, first things first, we shall focus on question 4.1. Right, and what is question 4.1? Both A and C occur. Calculate the probability of the following, that both A and C occur. But first things first, what do we know here? We know that A and C are what? Are mutually exclusive events. So if two events are mutually exclusive, then we know, right, that the probability of A and C is equal to 0. Why? Now we note that since A and C are mutually exclusive, right, are mutually exclusive, we say simultaneously there is no intersection. There is no intersection of A and C. Right, so in other words, we note that the examiner here asked the students to calculate the probability of the following events occurring. Both A and C occur. Now we know that we were told when the question was introduced that A and C are mutually exclusive. As a consequence, if two events are mutually exclusive, then the probability of both events occurring is identically 0. Any question?
No, thank
No
you.
question. Okay, we move to the next, 4.2. Calculate the probability of the following events. In 4.2, both B and C occur. Simultaneously, we check that B and C are, what kinds of events are these? B and C are independent events. Right, so what do we know about independent events? Right, we know that the probability of B and C is equal to the probability of B times the probability of C. Why is this true? It is because the events are independent. Whenever two events are independent, Whenever two events are independent, then the probability of both events occurring is the product of the probabilities of the two respective events. As a consequence, right, we know that B and C are independent, and the probability of both B and C occurring would be the probability of B times the probability of C. However, we know the probability of B and that of C, they were given to us. What is the probability of B? The probability of B is equal to what? It is 0,4. We write that one down. The probability of C is 0,2, precisely. So that the probability of B and C equals the product of 0,4 and 0,2. And we proceed to use our calculator in this case. Right, so we have the 0,4 times, or 0.4, 0.2, right? The 0.4 times 0.2 gives us what? Right, gives us 0,08. And we shall note, therefore, that the probability of B and C occurring is actually 0,08, given that both B and C are independent. Please note that if two events are independent, then the probability of both of them occurring is the product, right, of the two respective events. And therefore, we note, therefore, we write down 0,08. 0,08. Like so. Any question about independent events? This is the formula for independent events. When you are told that two events are independent, this is the formula. Always, always in the exam, this is the formula. Any question?
Can I ask, how do I show it in the Venn diagram? Is it also going to have an intersection or not?
Okay, that's a good question. How would you know in the Venn diagram, is it going to have an intersection or not? Yes, it is surely going to have an intersection. Why? Because if ever there was no intersection, then the probability was going to be 0. And that would mean the events would be mutually exclusive. Okay. Next point. We continue as follows. We continue as follows. 4.3. Now in 4.3, we're interested in answering the question about calculating the probability of the following events occurring. At least one of A or B occur. At least one of A or B occur. Obviously, at least one of A or B or both occur. So now, what do we do here? What formula do we use for this particular question? Right, so we are sure that at this point in 4.3, we shall have the probability of A or B. Right, you can write here the probability of A or B is equal to what? It is the probability of A plus the probability of B minus the probability of A and B. Please, this is the formula, but all the time, whenever we given two events, A and B, then we then say the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, what is this? We then say the probability, because now if they say the probability of at least, what does at least mean? The probability of at least one of A or B occur. In other words, it is either A occurs or B occurs. So it is A or B. And therefore, this equals the probability of A. This is the formula. Plus the probability of B minus the probability of A and B. Like so. What is this? Probability of A or B equal. What is the probability of A? It is actually 0, 3 plus the probability of B, 0, 4 minus the probability. So you have the probability of A, and obviously you have the probability of B as well. That of A is 0, 3, and that of B is 0, 4, minus the probability of A and B. Right, and we know that A and B, whenever they appear, we are back to the question. What do we know about A and B? A and B are independent. If A and B are independent, we proceed to then say, this is the probability of A multiplied by or times the probability of B. Why do we multiply the probabilities in A of A and B? Because we know that A and B are independent events, and therefore the probability of A or B equals, right, we already know this 0, 3 plus 0, 4. It's very, very straightforward. So what exactly do we say here? We can say this is 0, 7 minus. What is the probability of A? That of A we know is 0, 3 in parentheses times the probability of B, 0, 4 in parentheses. We want to determine, right? We want to determine the following, right? So we want to actually determine the products here, right, of A and B. So we can actually be in a position to do that with so much ease. And we can use our calculator. We can use our calculator. In which case, therefore, we know, right, 0.3 times 0.4, and this is actually 0, 1, 2. Right, so we have that therefore the probability of A or B. 0, 7 minus 0, 1, 2. What is the answer? Okay, we're back. We're right back. And we are using our calculator at the moment.
It's 0.58.
0.58. Wow, so smart. Well done. Very well done. 0.58. I trust you. Right. It is indeed 0.58. Well done. I trust you there. And see, it's a very rare skill in the learners, because now you see what happens is the students right 0.58. So the students normally rely on calculators, and therefore they cannot use their heads. Mental computations are no longer the order of the day. Right, so
Yes,
we
sir.
go. Right, so now let us continue to check these out. So it is 0.58, and therefore this is the probability of A or B. Right, it is 0.58 there. Any question on this one? Of at least one of A or B occurring?
No.
No question. We move forward.
Yes.
Okay. Right. When you learn probability, it's not only just the calculation of probability, but also the counting arrangements, counting techniques. Right. Like in question 5, here is the question. Consider the word product. The word given is the word product. How many different arrangements? So we're discussing the notion of arrangements. How many different arrangements are possible if all the letters are used? Have you ever done arrangements before?
We briefly touched on it in class.
We touched on it in class. Right.
Yes.
So now, what do you look for? What would you think the number of arrangements are in the word product? Number of arrangements.
Is it not 6?
Okay, that's fine.
I think.
Never mind. Okay, because we're looking at the word product. Right, so looking at the word product, there are a couple of things you need to take into account. But what are they? Let's look at the word product. The word product has the first letter, the second, the third, the fourth, the fifth, the sixth, the seventh. How many letters are there? We have a total of 7 letters in the word product. Now, if this is the case, we want to do the arrangements, and this is how we do the arrangements. To do the arrangements, we decide that we're going to arrange these here in a straight line. Okay, we can do that in a straight line, we can do that in a circle. Right, so we do it in a straight line. Right, so we do position 1, 2, 3, 4, 5, 6. And let's stand here so that we have 1, etc. Okay, proceeding in that direction towards the right. Okay, so it's fine. So in other words, we're going to have 1, 2, 3, 4, 5, 6, 7, like so. Right, and what are we able to see? We have a total of 7 letters. So now we then say if we are to arrange these letters here, we shall have to make choices. So now we then say the first letter to be put here, because how many different arrangements are possible? Right, so now if we want to make arrangements of these letters, we are speaking about the notion of permutations. Permutations, okay. So now we count 7 letters. The letter to be placed here, in how many ways can we choose the first letter from the combination here? Right, so in how many ways can we choose the first letter? So either we choose this one, so we are spoiled for choice, We can either choose letter 1, letter 2, letter 3, 4, up to 7. So in other words, we have 7 letters to choose from. So the first letter can be chosen in 7 ways. After the first letter has been chosen, doesn't matter which one. Maybe we chose the letter C, we cross it out. Then you're left with a total of 6 letters remaining. Then want to put a letter here, and to put a letter here, the letter can be chosen from 6 letters, and therefore we say it can be chosen in 6 ways, or we have a total of 6 choices, 6 letters to choose from. After that, after we have chosen that, it doesn't have to be in order. Out of 7, 2 have been chosen. So we'll have 5. From the 5 remaining letters, we can choose the letter in 5 ways. 5 ways, so you have 5 choices. Right, so after that, we're left with a total of how many? So out of the 7, I've chosen 3, and we're left with 1, 2, 3, 4. And from the 4 remaining letters, the letter that is there can be chosen. So in other words, we have 4. We had 4 choices here. After that, that one has been chosen. Then we have how many, for example? We have 1, 2. Right, so just check that out. Just check that out. So now we had actually had 4 choices when there were 4 letters remaining, and we had 1, 2, 3, 4. Right after that, we cross one out. Right, so we had 1, 2, 3, 4. We cross one out, we're left with 1, 2, 3. We have 3 choices to make. After that, we have 2 choices to make. After that, we have 1 choice to make. In other words, we say, okay, the letters can be chosen in 4 ways, 3 ways, 2 ways. One way. So, right now, the question remains. The question still stands. But the question is, how many arrangements are possible? Take a look at this question and reason with us. Take a look at this question and reason with us. The number of arrangements. Number of arrangements. Number of arrangements. Right, number of arrangements. Right, what is the number of the arrangements? So the first one can be chosen in 7 ways. After that, the next one in 6 ways. Or we have 5 choices, 4 choices. According to this, 3 choices, 2 choices, 1 choice. So now this is called the 7 factorial ways. So 7 factorial ways. It means, therefore, we have a total of the following. We have a total of the following. Right. So in other words, we have 7 factorial, or use your calculator and you say 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is actually 5,040. 5,040. Any question on the different arrangements possible if all letters are used?
Can I ask, in like
Yes, please.
in the exam, can I just write 7 factorial and then give the
Yes, you
answer
can be able
afterwards?
to write just 7 factorial, and then you get the answer. Yeah, because the examiners do not expect a lot of detail. Because in the exam, you're not a teacher there. You are a student, so you need to just write the answer they want.
Okay.
Yeah, we are just explaining because we are trying to make sure that this makes a bit of sense.
No, it's fine.
All right, but also you need to note that this is true. How many letters are the same in the word product? How many P's are there?
None. There's
Okay,
only
there's only
one.
one. How many R's are there? There's only one. How many O's? One, 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 one. So each letter occurs once, and that is why this is possible. We're going to look at cases when the letters are repeated. The letters can be repeated. Like in some words, you'll see that in some words the letters are repeated, the arrangements become different. They become different if their letters are repeated. Okay, like in the word good, there are 2 O's, and the arrangements cannot just be 4 factorial, for example, because there are 4 letters in the word good. So they can't just be 4 factorial. We shall discuss that. Let's move to the next question. 5.2, how many different arrangements can be made if the first letter is T and the 5th letter is C? So the examiner is now cunning, but he's very smart. He's saying, hang on, I want to give you some rules of the game. Letter 1, 2, 3, 4, 5, 6, 7. Right, so now we then have the following here. So what then do we have here? Now they said how many different arrangements? Different arrangements can be made if the first letter is what? It's T, and the fifth letter is C. So they're saying the first letter is T, so you put T here, and the 5th. So you count position 5, and the 5th letter is C. So the first and the 5th letters are what? These 2 letters have been fixed. You fix them, you fix these positions. In other words, these ones here are actually immobile. You can't move these. You can't change this. So in the word product, then it means that you cut out the T, you cut out the C, and you are left with how many letters out of the 7? Because we removed 2. Out of the 7, we removed 2, so we're left with 5. So in other words, we can deal with Proda, and the CT are gone. C and T are out of the picture. They've been removed. Now, it means that we're left with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 letters. That's what we're left with. If we are left with 5 letters, in other words, here, how many choices are we going to have? We're going to have 5 choices to make. After that, we choose one letter, maybe P. We're left with 4 letters. We shall then have 4 choices to make. After that, left with 3 letters. Shall have 3 choices to make. We can choose D, left with 2. Right, we have 2 choices to make. Right, maybe we choose O. We're left with U. We have 1 choice. Only 1 choice. And therefore, how many different arrangements can be made? Right, so the arrangements that can be made will be 5. Right, times 4. So for 5.2, the number of arrangements. Right, the number of arrangements. Right, the number of arrangements is equal to 5 times 4 times 3. 5 times 4 times 3 times 2 times 1. And this is exactly 5 factorial ways. We go to the calculator. We know that it's 120. I'm sure you can be like, okay, but we're very much used to that. You know probability already. And therefore, you know that it is 5 factorial, but 5 factorial is equivalent to what? Actually, it is exactly 120. Right. And then you'll be like, okay, now I know. So yeah, here's the factorial on the scientific calculator. So you have 5 factorial, and that is 120. Right. So in other words, we have 120 possible arrangements here. 120 possible arrangements here. Okay, yeah. Do we have to write all these? No. The answer we want is number of arrangements is 5 factorial. So you can just write in the exam under exam pressure. Right. In the exam, you just say number of arrangements. Number of arrangements. Right. And you say number of arrangements is 5 factorial, and that is, you can even just say 5 factorial and stop there. Or you can say 120. You can say 120 as well, in which case, therefore, 5 factorial is quite sufficient. But I must indicate it is standard practice for the examiners to write out the output. If you say 5 factorial, they normally say do it on the calculator and give the output. So please always give the output because the marks are 2. But now look, what if they give 2 marks? What do they mark here? So what they mark here is the following. They mark the 5 and they mark the factorial. So they mark the 5 and then also they mark the factorial. And the marks are 2 here. There are 2 there because they mark the 5 and they mark the factorial as well. The 120 is extra. You might decide not to write it. You can only write it if you have the time. But oh, I know, in the exam, you do not have the luxury of time. And that is something very important. It's something to take note of. Any question on this?
No,
No
thank
question,
you.
move forward. 5.3 asks a question. How many different arrangements in 5.3, how many different arrangements can be made if the letters R, O, and D must follow each other in any order? How many different arrangements can be made if the letters R, O, and D must follow each other in any order? What is your take? Okay, let's do this together. So in other words, we're looking for the number of different arrangements, right, that can be made if the letters R, O, and D must follow each other in any order. Okay, I want us to take this into account. So we're looking at the word product. We're looking at the word product, but we're singling out some letters. We are taking out R, O and D must follow each other in any order. So in other words, right now we then say, okay, we single out, but if we take out R, O, and D, how many letters are we going to be left with? So in other words, we have P, R, O, D, we put them, they become one thing. They become one entity. And then we have act like this. Okay, take a look at that. So we take the word product, ROD are grouped together, and then we have UCT sitting outside. The P is in the beginning. So now we have 1, 2, 3, 4, 5 things to deal with. Right, we have a total of 5 objects to deal with. 1, 2, 3, 4, 5, meaning the number of arrangements. Meaning the number of arrangements. The number of arrangements is equal to what? We start with the ROD. How many letters are there? There are only 3 letters, and these 3 letters can be organized in 3 factorial ways. And after that, we're left with PUCT, right? But also, after organizing this, we then say we have 1, 2, 3, 4, 5 letters. But each of this is like 1 letter. It's right as 1 letter, the ROD. In which case, therefore, the 1, 2, 3, 4, 5, and therefore we have 5. But all of these are different. P occurs once, U occurs once, C and T both occur once. These ROD occurs once, and therefore we have 5 factorial ways of organizing this. And therefore, what do we have? Right, so we know 3 factorial is actually a 6. So in other words, if you're going to do 3 factorial, it's a 6. And then we have already done 5 factorial before. We remember, it's 120 simultaneously. So we have 6 times 120, 720. And therefore, we have exactly the following 720 arrangements. Any question on these 5.3? Any question?
Can I ask,
Yes,
when
please.
you say 3 factorial, right?
Yes.
Does that mean that the ROD can be arranged as well
Yes.
in a
First,
different arrangement?
yes. So, in other words, in principle, what we need to do is to say we start with the ROD 1, 2, 3. Normally, if we show the steps a little bit, right, we're dealing with the ROD. If we want to arrange the ROD, we have 3 letters. For the first letter to put in the first position, we have 3 choices. After we have chosen 1 letter, we're left with OD. We have 2 choices. And then we have 1 choice. So in other words, to arrange the ROD by itself, meaning the ROD can not only be ROD, because now we're getting more options. So the ROD can be anything. What can it be? So for the first, the idea is, if we're dealing with the ROD, right, so for the first letter, if we arrange the ROD, the first position can be R, the next one can be O, and the next one can be D. So obviously for the first letter, we actually are sure that we have 3 choices to make there. All right, so that is something that becomes so important. As a consequence, we have 3 choices. After the R has been chosen, we have 2 letters, we have 2 choices. And then we have 1 choice. 3 factorial multiplied by, now we put the ROD and say, okay, if we arrange this ROD in any order, then we have 1, 2, 3, 4, 5. We have 5 choices, and therefore we have 5 factorial possible arrangements, and therefore we have 720. Right, so what exactly do they mark in this one, in the marking center? They mark the following. They give the mark for 3 factorial. They give the mark for 5 factorial. And they give the mark for the multiplication. So that this one be given 3 marks. Simultaneously, if you write the 720, obviously, which is the best. Always write your answers. Your calculators are as fast as lightning. They can't waste your time. They are there to help you, to give you answers that will earn you marks and earn you the distinction that you need the most. So we continue as follows. Right, so we continue as follows. Right, so we proceed as follows. Any question? No question?
No question.
All right, we move forward. Now, something that is very important is the notion of what you call the Venns. Venn diagram. Venn diagram. Right. Okay, now the idea of Venn diagrams is very important. The idea of Venn diagrams is very, very important. Let's look at the Venn diagram. A survey is conducted among 174 students. The results are shown below. A survey is conducted among 174 students. The results are shown below. So you have 37 students who study life sciences, 60 study physical sciences, 111 study mathematics, 29 study life sciences and mathematics, 50 study mathematics and physical sciences, 13 study physical sciences and life sciences, 45 do not study any of life sciences, mathematics, or physical sciences. X students study life sciences, mathematics, and physical sciences. Draw a Venn. Draw a Venn diagram to represent the information above. Let's look at the Venn diagram here. We need to draw a Venn diagram and it's going to earn us marks. What is the Venn diagram here? Okay, we started this very easy. We start at the center. The practice is to start at the center. X students study everything. Life sciences, mathematics, and physical sciences. Right, so in other words, we have the following here. So if we then say we have this one that studies life sciences. So if we call the subject A, life sciences. Right, so subject A is life sciences. And then we have subject B, doesn't matter. Let's call this one life sciences. Let's call this one physical. Physical sciences. And we call this one here mathematics. We have this one called mathematics. Like so. Now, life sciences, physical sciences, mathematics. Now, we continue to analyze this. As said, we normally start at the center. X students study life sciences, mathematics, and physical sciences. So there are those who study everything. They are sitting here at the center. So at the center, they study entirely every single bit of thing. But we note, therefore, that in this Venn diagram, we have the following. Right, so with this something we call the universal set. Universal set. So we cover every single bit of thing, put everything in the rectangle like so. But X studies the life sciences, the physical sciences, the mathematics. Right, moreover, So we're done with the X. What else do we have? Right, we begin migrating away. We realize that there are 13 students that study physical sciences and life sciences. 13 students study physical sciences and life sciences. Right, so you look at physical sciences and life sciences, and those are 13. So here you have 13 minus X, because physical sciences and life sciences are 13. But you say from 13, you minus X for all those for the students who do everything, all three learning areas. Okay, we proceed. After this now, you then take a look at the next point. Right, looking at the next point, what more are we able to extract from this particular Venn diagram here? Right, you look and think, there are 29 or there are 50, doesn't matter. Right, doesn't matter which one you start with. 50, study mathematics and physical sciences. 50, study mathematics and physical sciences. Let's check. Mathematics and physical sciences. Right, we have mathematics and physical sciences. Right, so if you look at mathematics and physical sciences, they are 50. Right, so which means here you'll have 50 minus X. 50 minus X. Right, so those who study mathematics and physical sciences are 50, so that you're going to have exactly 50 minus X. So we continue as follows. Right. Next. There are 29. 29 study life sciences and mathematics. 29 study life sciences and mathematics. Life sciences and mathematics. There are 29. 29 minus X. So that those who study mathematics and life sciences are 29 minus X. So we have catered for the 29. Right, so there are 45 students who do not study any of life sciences, mathematics or physical sciences. 45 of them, they don't study any of those. So those 45, we put them outside. They do not study life sciences, they don't do physical sciences, they don't do mathematics as well. They're 45. You put them outside, but you put them in the rectangle, in the universal set. Right, and we move forward. We proceed. What else do we need? How many students study mathematics? There are 111 students that study mathematics. 111. Let us check. So in other words, in mathematics, if you add everything here, you must get 100 and what? And 11. So in other words, you would say, okay, put a Y here, like that, and then do some rough work and say Y plus 29 minus X plus X. Y plus 29 minus X plus X plus 50 minus X is equal to 111. Y plus 29 minus X plus 50 minus X. So now you do some rough work. Minus X and X gives 0. Right, and you are left with a single X. But you have exactly what? You have exactly 29 You have exactly 29. Let's check this. Right, so you have exactly 29 and 50, 79. So in other words, y is equal to 111 plus x. You move the x to the other side, making it positive, and then minus 79. So now you can use your computer, your calculator. Dealing with doing some rough work here. We're doing the Venn diagrams. Please pay attention because students get lost here. In this detail, you need to read the story. 111 minus 79. What do we get? We get 32. 32. Right, so it becomes 32 plus x. So we get exactly 32 plus x, meaning here in the place of y, you're going to put actually 32 plus x. Take a look. You can even do this mentally. So we have 32 plus x, like so. So this one was some rough work. You don't need to put the rough work in the Venn diagram. I'm just doing it for clarity purposes, for clarity's sake. Okay, but yeah, the examiner gave us more information. Let us check. 60, study physics, physical sciences. 60, study physical sciences. So in physical sciences, there must be 60. So you can put a Y here like this. Doesn't have to be a Y, please. You can put a P for physical sciences, like P. So in other words, you do some rough work on the side, but please, all rough work cannot be done on paper to be thrown away. All rough work must be done on paper in your answer book. Please, students, make sure that you do not throw your rough work away because you are not in the exam just to pass time. You are there to gain marks. You can't just be writing things to throw away. Don't do it in the exam. So we have this plus this plus that plus that. It's 60. So that in the end, what do we obtain? We have minus x and x giving us exactly 0, 50. Together with 13, it's 63. So we have actually the following. 60 minus 63 plus x. P equals x minus 3. This is the result. Right. So we have P x minus 3. In other words, x minus 3 students only do physics. They do physics only. Okay, pay attention. We move forward. But now we can remove the P here and we can actually remove the rough work from the Venn diagram because now it has served its purpose and we continue. Next. What do we have? We want to find the number of the students who are only doing life sciences. How many? There are 37 of those who do only life sciences. They want to be medical doctors. They want to understand human anatomy and physiology. Let's call them L. In other words, we're going to take L for life sciences, 29 minus X plus X. So we add everything here, plus 13 minus X. The result is 37. Right, because we know 37 study life sciences. If 37 study life sciences, we are sorted. Right, so we know we want L, and therefore let us do some rough work. Right, so minus X and X cancel out, from which we're able to obtain 29 and 13 would give us what? 42. 42, but it becomes negative, taken across the equal sign, meaning we have 37 minus 42 plus x, negative 5 plus x, meaning this is actually the same as life sciences. It is x minus 5. X minus 5. X minus 5. All right, so we're good. We're good. Right, so yeah, we sorted there. We sorted. Yeah, so we have exactly this. The question was draw the Venn diagram. And, right, we have drawn the Venn diagram. And what is the Venn diagram? This is exactly the Venn diagram. Life sciences, you have x minus 5, 29 minus x, x and 13 minus x. 45 don't do any of the subjects. Physical sciences has x minus 3, has 13 minus x, has also x, has also, right. So yeah, that's what we have. So for physical sciences, you have exactly the following. 50 minus x, x and 13 minus x. Mathematics, 32 plus x, 29 minus x, x and 50 minus x. Any question on this Venn diagram?
No,
No question.
no.
All right, we move forward. Right, the first question in 6.1 was obvious. Draw a Venn diagram to represent the information. We'll spend some bit of time there. Hang on, we're gonna do more Venn diagrams, please. This was just one practice question, but just to help us, sort of remember this. But yeah, there are tons of questions on Venn diagrams. Show that x equals 13. Show that x equals 13. Right. So the examiner is saying show that x equals 13. So the only actually hold on point is the fact that a survey is conducted among 174 students. 174 students. So we're good. Let's come to the Venn diagram. So if there are 174 students, we're going to start as follows. We're going to start in saying, we can start in any of this. We can start with the life sciences and say, x minus 5 plus 13 minus x plus x, right, plus 29 minus x. Let's start. So we're going to start by saying, let's do this. Right, so we're going to say exactly x minus 5 plus 13 minus x, x and 29 minus x. Right, plus 13 minus x plus x.
Plus 29
Plus
minus x.
29 minus x. Well done.
Plus
Plus,
15 minus x.
what is the next one? You have
50
exactly
minus
50 minus x, right? Plus 50 minus x plus. What is the next one?
x minus 3.
Right, we also have x minus 3. Right, we also have x minus 3 plus what?
X. No, 32 minus x.
Plus 32 plus x.
Plus x, sorry.
Okay, good. 32 plus x plus what?
45.
Plus 45. Very well done. Plus 45. And the result is 174. Right. We good. We so good. Right. We are most certainly doing very, very well here. If you add everything, what do you achieve? X plus, okay, let us do some cancellations here. This, that. So what are we left with? We're left with only one x, a single x term. We're left with only a single x. Then we shall add everything is 174. Ah, okay. We're good. All right, so yeah, let's do this. So now we're gonna start and say minus 5 plus 13 plus 29 plus 50 plus. Okay, we delete. Minus 3 plus 32 plus 45, 161. So this is exactly 161, meaning X is the same as what? The difference. Right, so now it means therefore that we have that X is equal to 174 minus 161, and X equals what? X equals exactly 13. Any question on this? Because we're to show that X is 13 and we got that X is 13. Any question?
No,
No
nothing.
question.
Yeah.
Move forward. Thank you. Right, in the next question, they're saying that there are students that are naughty. If a student was selected at random, calculate the probability that he studies the following: mathematics, physical sciences, but not life sciences. What is the probability that is required over here? The student is doing mathematics, right? Is doing mathematics and physical sciences, but not life sciences. What is this probability? The probability that the student is doing what? Is doing mathematics and physical sciences, but not life sciences. Let us check that. So this student here is doing what? Is doing mathematics and physical sciences, but not life sciences. So what is that the student, let's check this one here. So now, what exactly would that be? It is clear in the Venn diagram anyhow. So if you are to do mathematics and physical sciences, and we are saying to you, hang on, take out the life sciences. So what would that be precisely over here? Right, so mathematics, physical sciences. So what is X here as a consequence? We know that X is 13, so you have 50 minus X. Just write a little bit more step here. 50 minus X, which is 50 minus 13. What is 50 minus 13? 37. 37. So in other words, here you'd have 37 when X is 13, so that you come here. So this would be 37 divided by the total, 174. And we take a calculator to find the probability, because we are discussing probability today. And therefore, the probability is what? Remember, we're here for the next 2 hours. We're here until 8. Right, so we have 37 divided by 174. And the answer is what? Is actually 0.21. 0.21. 0.21. Okay. Any question? Any question? No question. We move forward. We move forward. Right.
Yes, sir.
Okay, good. We move forward, and our aim is to practice as much as possible today. We are going through this topic. We want to make sure that we leave no stone unturned. Every question will be done. Every question will be done. We move forward. Okay, the next point. In 6.3.2, the examiner asked a question, asked the student who dealt with this probability question. Only one of mathematics. If a student was selected at random, calculate the probability that he studies the following. Only one of mathematics or physical sciences or life sciences. So now let us do this. The student studies only one of mathematics or physical sciences or life sciences. Right, so at this point, You then calculate the probability of only math, only mathematics, or physical sciences, or life sciences. And this is exactly what. So if it is only mathematics, or physical sciences, or life sciences, let us check in the Venn diagram. So you look at the Venn diagram and you then say it is only mathematics, or physical sciences, or life sciences. So it must be 32 plus x, or which is plus this plus this. Right. So in other words, it will be 32 plus x. You can write here 32 plus x plus. So you do the 32 plus x minus 5 plus x minus 3. So you're going to do here x minus 5 plus x minus 3 all divided by the following. Right, a total of 174, which is the probability of only mathematics or physical sciences or life sciences. So if x is 13, it means you're just going to be plugging in your numbers there as a consequence. Right, so you have 32 plus 13. You have 13 minus 5. You have 13 minus 3 all over 174. 32 plus 13 gives us a 45 plus 13 minus 5 gives us exactly 8 plus 13 minus 3 gives us 10, all divided by 174. And the total is what? So you're going to use a calculator as follows. Right, so the calculator is here. And we're going to do the top. And then say, for instance, you can do 45 plus 8 plus 10. You can do this quickly to a 53, 63. So you have 63 over 174. So you have exactly 63 divided by 174. What is the answer? This is what we get. This is what we get. 63 out of 174. The calculator simplifies it to 29 out of 58. 29 divided by 58. 21. 21 divided by 58, which is 0.36. So this is 21 divided by 58, which is 0.36. And this is the probability that the student does only one of mathematics or physical sciences or life sciences. Any question on this so far?
No.
No question. We move forward. Let's deal with the codes. Now, there is the digits. There are digits that are very fascinating and they keep us excited in mathematics, and we are happy to deal with them. Right. We're happy to deal with them. The digits 0, 1, 2, 3, 4, and 5, and 6 are used to make 3-digit codes. The digits 0, 1, 2, 3, 4, 5, and 6 are used to make 3-digit codes. How many unique codes are possible if digits can be repeated? Okay. How many unique codes are possible if digits can be repeated? Okay, we're good. Let us check this question out. Right, now if you are to deal with this question, the number of the unique codes, remember that we are to make 3-digit codes in 5.1. So the number of the unique codes, number of unique codes, right, number of unique codes equals how many unique codes are possible if digits can be repeated? 3-digit codes. So now if you're dealing with a 3-digit code, it means that you're going to have places like positions here. 3-digit code, how many digits are there in this case? Remember, these are codes. These are not numbers. They are codes. Dealing with the codes is different from dealing with numbers. So in other words, dealing with a code, how many digits are here? 2, 4, 6, 7. Codes can start with a 0. Codes can start with a 0, meaning that if we are to deal with the codes, we have 7 choices to make for the first digit. We can start with 0, 1, 2, 3, 4, 5, or 6. Right after that, we can repeat because these are repeated. So we can still try and put any digit here. So we are spoiled for choice. So we have 7 choices. We have also 7 choices. Digits can be repeated. We are dealing with 3-digit codes, and the code will have 3 digits, a digit here, a digit there, and a digit there. So meaning that we have also 7 choices. Now, take a look. What is the number of the unique codes? Number of unique codes. It's going to be 7 times 7 times 7. And 7 times 7 times 7 is 7 cubed. And 7 cubed equals what? 3, 4, 3. 3, 4, 3. So the number of how many unique codes are possible if digits can be repeated? 343 unique codes. Any question on this one so far? So what do you write in the exam? You can just write a number of unique codes. Then you write 7 by 7 by 7, which is 7 cubed. And 7 cubed is 343. Any question?
No, sir.
No question. We move forward. 5.2, how many unique codes are possible if the digits do the following? They do the following bump jive. They are doing what? If the digits cannot be repeated. This time around, we're saying, hang on, we can't repeat the digits. So, in other words, we're going to do position, 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 3-digit codes, position 1, 2, 3. So now, digit 1, digit 2, digit 3, 3-digit codes, but these cannot be repeated, meaning that digits now, codes are not numbers. These are codes. Codes can start with 0, like the area code of a telephone. 012 for Pretoria, 011 Johannesburg, 015 Polokwane, something of that sort. And you get all this. 021 Cape Town, you name it. So as a consequence, codes can start with zeros, but now if they say count the number of people in a house, well, we don't normally say, if they say it's a 3-digit number, you can't say there's 002 people in the house. Because this one, we say it's a 1-digit number. 2, it's a 1-digit number. So now, because they can trick you with this in the exam, the codes and numbers, please, students, pay particular attention. The examiners can be tricky sometimes. They want to get you. They're out there to get you. Right, so how many unique codes are possible if the digits cannot be repeated? So now they can't be repeated. It means that out of 0, 1, 2, we're taking them from here, 0, 1, 2, 3, 4, 5, and 6. So now we spoil for choice and say, okay, we have 7 choices to make for the first one. We have 7 choices to make. After that choice has been made, remember, cannot be repeated. If we chose 0, we'll have 6 digits, from which now we have 6 choices to make. After that, maybe we choose 5, we're left with out of the 7 we had, 2 have been removed. We have 5 choices. We have 5 choices. We have 6 choices here. We have 5 choices. Meaning that the number of unique codes, okay, the number of unique codes, right, we're dealing with probabilities and codes, the number of unique codes without repetition, without repetition is equal to what? Okay, so without repetition, we compute as follows. So we have 7 choices times 6 choices times 5 choices. We use a calculator, and now we can be in a position to compute these precisely. So you can use our computer. I know you can do it. You can do it mentally and be like, okay, I know 7 times 6 times 5 is 210. So we have 210 such codes. You have exactly 210 such codes. Any question?
No, sir.
No question.
Oh, no, wait. I actually have a question.
Okay.
There was, I think, with my teacher, we did the one with the factorial, like it's the number factorial over like
Yes,
two
yes,
ways.
you can always do that one. In other words, you can do it like this, or you can actually use the fact that how many letters are there all together here? Right, we
So,
said there are 7 of them, right? So you have
mhm.
7 digits. So you use the 7 factorial divided by, now you are then saying, obviously, because the digits cannot be repeated, but now you are dealing with 3-digit codes, meaning from the 7, you're going to extract. You're going to extract in any random order, so you can remove 3. You need to remove 3 of them. So you pick 3 out like this. Right. So if you pick 3 out, the question is, how many are you left with? Remember, you have 7. You minus 3 from 7, you're left with what? You're left with 4. Right. So now you would put here 4 factorial. You'll put here 4 factorial, which is what remains, therefore, when you have the 3 digits taken out. Right. So in other words, you have a total of 7 digits. So the total arrangements are 7, but obviously we're saying there are no repetitions. There are no repetitions, and therefore you have 7 factorial. Right. And after having had 7 factorial, then you come and then say you have a total of what? 3-digit codes. Right. Now, if you cannot repeat, you can then be in a position to then say, what then exactly do you do? Because you are dealing with 3-digit codes, right? You can see that out of the 7 letters, you remove 3, right? And if you remove 3, you have 7. You have rather 4. 7 minus 3 gives you 4. 1, 2, 3, 4. Right. And that obviously would be obviously what you do. Or simultaneously, what you do is the following. Right. You can then say you have the following. So if you have 1, 2, 3, right, you have 1, 2, 3, then the other one is going to come from this group. It's going to come from this particular group. And if it comes from this particular group, so this is the group of the remaining ones, meaning that you have 1, 2, 3, right? And after you have 1, 2, 3 codes, you're left with 4. You're left with 4 choices that can possibly be made. So obviously you have 7 factorial of all those, and then you have 4 factorial. If you're then saying, obviously, you have no repetitions allowed. Any question?
No,
Okay,
thank
we
you.
proceed. Okay, but I must indicate that the answer is the same. Just to mention. Doesn't matter. Okay, so you can then say 7 factorial divided by 4 factorial. Right? It is still 220. Rather, 210. 210. 210. So it's still the same thing there. It's still actually the same thing there. All right. All right. Any question?
No, thank you.
All right. All right. All right. All right. All right. All right. We continue. Now, if you look at the next 5.3, in the case where digits may be repeated, how many codes are numbers that are greater than 300 and exactly divisible by 5? Greater than 300 and exactly divisible by 5. Okay. Now, I want us to look at these and think of these carefully. I want us to think of these and to be very careful of this. So if they then say in the case where digits may be repeated, how many codes are numbers that are greater than 300 and exactly divisible by 5? Let's check this. Right, so here is the question. So now if they're to be greater than 300 and exactly divisible by 5, so we have a couple of restrictions here in 5.3. So which means, therefore, here you have the number of codes. Right, now you have 0, 1. I want us to do this a bit more carefully because there are more restrictions. You need to understand this. 1, 2, 3, 4, 5, 6. So, I want us to look at the fact that you would have the following. Okay, right. So if the number will be greater than 300, a number greater than 300 and divisible by 5. But in the case where the digits may be repeated, okay, a little bit tricky, but because now we have a bit more restrictions, but I want us to go slowly and build understanding here. Okay, greater than 300, you start. Greater than 300 in the true sense of things can include 300, can include 400, 4, 5, 6. Like this. So now in this case, you'll have the following. Let's reason these together because it's a very interesting one, but you need to build understanding here. For the first position, you can, the first digit, for the first digit, if this is a, because in the case where digits may be repeated, but we're still dealing with the 3-digit codes. But with the 3-digit codes, in the case where digits may be repeated, how many codes are numbers? The codes that have to be numbers. Now, not all codes are numbers in the true sense of it. But here, the examiner is clear that the digits can be repeated, but the codes are numbers that are greater than 300. A number greater than 300 can be like 301, for example, 302, or 400. But now a number greater than 300 can essentially start with 300. So now we have how many choices? Four choices to make. We have 4 choices to make. Because if these numbers are 3-digit numbers, but they can be greater than 300, the number can be like 301, can be 400, can be 500. If it starts with 5, can be 600 if it starts with 6. You get it? Okay. Yeah. Next. Okay. After that, you then say if the number is greater than 300, it can start with any of these. But now the number in the middle, if it starts with any of these, 300, 4, 5, 6. Okay, then what is the next digit? The next digit can be anything. The next digit can be anything, meaning that you can put, it can be 301, in which case then the digit in the middle can be 0, can be 1, 2, 3, 4, 5, 6. So you have 7 choices there. 7 choices. After that, then you then say, oh, you must be careful with the last one, because if the first digit is 3 and the next one is 0, then
So,
this one, yes, please.
before you continue, can you please explain the 4 choices again? Why can't it also be 7?
Oh, okay,
Because
okay, that's fine, yes. Okay, right, let me explain the 4 choices. Because remember that there's a restriction that greater than 300. Greater than 300, you want to form numbers that are greater than 300. Greater than 300, numbers greater than 300 can start with 3, with the digit 3. But now, the important digit can be like the last one. That is going to make a difference, for example. But the number greater than 300 cannot be 300 again. So it can start with 3, 300, 400, 500, but not just 300, greater than 300. It can be like 301, 302, 303, and so on. So a number greater than 300 can essentially start with 3, in case it's 301, or it can start with 4. Then it becomes 400, because 400 is greater than 300. Or it can start with 5, 500. Or anyhow, obviously the digits, in the case digits may be repeated. Digits may be repeated, so we can form numbers like 300. You know that. Okay, we can form digits like 500 because we can repeat the zeros. But obviously now, greater than 300, we can start with 3, 4, 5, 6. We can 2, 4. We have 4 choices. 1, 2, 3. But we can't start with 2 because the number can be like 200. 210, 200 and that. Those 200 and something, 100 and something, starting with 1, are all of them less than 300. Right. So we have 1, 2, 3, 4. So we have 4 choices for the digits that are 3 or more to produce 3-digit numbers that are greater than 300, like 301, 302, 310, whatever the case. But now if we form these numbers, 3-digit numbers, 3-digit codes that are numbers, now the number in the middle, because we're forming 3 digits. Now we must be very careful, because if we want to form numbers greater than 300, we are then saying, oh, the one in the middle here can be like 30, because then we can just change the last digit and make it a 1. Because if it's 301, then it's greater than 300. So it means, therefore, we have 7 choices. 7 choices here. 7 choices. 7 choices meaning we can put 0 in the middle, meaning 301 is possible. 302, 305, 307, 308 is possible. You get the point? So it means that we have 7 choices. For the one in the middle, we can put any of the digits here, like 301, 401, 402, and so on. Let's deal with the last one. But with the numbers that are greater than 300, right? Greater than what? Greater than 300. we then say for the last digit, but they must be divisible by 5. We could say, okay, greater than 300, we could do this. We could say, okay, greater than 300, okay, we just remove the zero there might be problematic in the case we form 300, for example, because we'll get a number that is equal to 300. But a number equal to 300 anyway, it's obviously not really greater than 300. But now the numbers are divisible by 5. Divisible by 5, the numbers that are divisible by 5 end in what? They end in what? The numbers that are divisible by 5 cannot end in 6. The last digit cannot be 6 because like 16 is not divisible by 5. But numbers like 15, yes. So a number divisible by 5 can end in the digit 5. But a number that is divisible by 5 cannot end in 4. So 4 is out. They cannot end in 3. Be 43. Numbers like these cannot be divisible by 5. So 3 is out. 2 is also out. 1 is also out. But 0, yes. So in other words, the last digit for the numbers to be divisible exactly divisible by 5, so would have 2 choices. The last digit for them to be divisible by 5 can be 0, like 10. 10 is divisible by 5 because 10 divided by 5 is what? Is 2. 20. 20 is divisible by 5 because if you divide, you get a 4. But now also 15 is divisible by 5 because if you divide, you get 30. So numbers divisible by 5 can either end in 5 or in what? Or in 0. Meaning we have 2 choices. We have 2 choices here. Okay. So we have 4, 7, 2. And then now we remove one case. We remove one case. What is the case? Because they must be greater. As said, we can form that 300 there. Because we can start with 3. Because we have 4 choices, the 3 is included in the 4 choices. We can have 3. From the 7 choices, you can choose anything. You can have 0. And then if we say the last digit can be 0, then we have 300. 300 is not greater than itself. It's not greater. The number must be greater than 300. So we must remove one case there. We must remove one case there. So that as a consequence, this is what we have. This is what we have. So it means that the number of codes in 5.3, 5.3, the number of the codes. Number of the codes. This is probability theory. Number of codes. So you need to reason and reason logically. Number of codes required. Okay, please, it's 5.3. It is 4 times 7 times 2 minus 1. 4 times, now what is 2 times? Okay, maybe 4 times 7 is 28. 28 times 2 is actually 56. Minus 1 is exactly 55. So the codes are 55. Any question?
No, sir.
Okay. So yeah, you need to think. We have to do more and more of this. But let's proceed and enjoy ourselves. Oh, yes. Something you need to note is that sometimes we're interested in the two-way tables. Two-way tables. Now, these are the skydivers and the guys who love aeroplanes. They like diving from the sky. In a survey, 1,530 skydivers were asked if they had a broken limb. The results of the survey were as follows. The results of the survey were as follows. Male, female, total. Broken a limb, not broken a limb, total. The numbers are there. Calculate the values of A, B, C, and D. Calculate the values of A, B, C, and D. what would A be? Okay, now we're looking at the fact that broken a limb, the total is 913. So which means that to find A here, we're going to simply say 463 plus A is 913. This implies that A is 913 minus 463, and the result is what? Okay, I can just use a computer here, calculator. I know you can do it mentally, possibly. Right. So we have exactly the following. 913 minus 463, 450. So which means that A is 450. But we also need a B, for instance. So A is 450. We also need B, but although the total here is 472, meaning that we can say 463 plus B is 782, which means B is 782 minus 463, and the result is what? Right, 782 minus 463, 319. So B is exactly 319. And then now when we got that B is exactly 319, we can easily get C because it is this plus that, which is exactly that. So in other words, we have 319 plus C is 617, which means therefore that C is 617 minus 319. And what is this? What is this? 617 minus 319. 298. So C is actually 298, meaning our A is what? Our A is 450 and our C is 298. Our B is 319. Our C is 298. Okay, we're not done yet. Our D as well. You add these two. Right, meaning that at this point, what can we achieve? We have 782 together with D, which is exactly 1530. D becomes the difference. Let us check the difference. Which means that you have 1530 minus 782. 748. 748. D is 748. Okay, so D is 748. So the question was, calculate the values of A, B, C, and D. A is 450, B is 319, C is 298, D is 748. Any question on this one so far?
No, thank you.
Okay, these are two-way tables. I will expect you to participate here in the next question when you do probability calculations based on tables.
Okay.
Right, now in 5.2, calculate the probability of choosing at random in the survey a female skydiver who has not broken a limb. A, we saw, is 450. I'm not going to waste a lot of the time there. B is 319. C is 298. D is equal to 748. Calculate the probability of choosing at random in the survey a female skydiver who has not broken a limb. Your take. What is that probability? So we are then saying in this one, you're thinking about it in the meantime. I'm just writing probability of female. I'm not writing quite the answer in full, but I'm writing the beginning of the quiz of the answer. Right. So the probability of female who has not broken, who has not broken a limb. Right. So the probability of a female who has not broken a limb. What do you think the answer is going to be?
Do I not say 298
298. Very well done. 298
over
over
over 1,530 or 600?
1,530. Well done.
Okay.
Well done. Okay, I was just testing you. I wanted to see what you're going to do. Okay.
No.
Yeah, I wanted to see if you're going to be able to read the values from the table. So, yeah, this is exactly our answer. So now you can take a calculator and then say, right, so you have exactly 298 and it is divided by 1530. And you have 149 divided by 765. You have 149 divided by 765 like this. Any question? All right, obviously you can write this as a decimal, meaning that you can do the following. Right, so you can write this in a decimal and then say SD button, which is actually 0.19, two decimal digits, 0.19, two decimal digits. This is the probability of choosing at random in the survey a female skydiver who has not broken a limb. Next question. Right, in the next question, we proceed to say A is 450, B is 319, C is 298, D is 748. Now, is being as you know, we're doing 5.3 now, and 5.3 says is being a female skydiver and having broken a limb independent. Use calculations correct to two decimal places to motivate your answer. Okay, let us reason these together. So now, the probability of female and having broken a limb. So we're going to do the probability. Female and broken a limb. Broken a limb. Right. What is the probability of female and broken a limb? Right. So what do you think of that one? Female and broken a limb.
450
Well done. It is 450.
over
Divided by what?
1,500.
1,530. Right. Simplifying these gives us exactly 5 divided by 17. We're using decimals, and therefore, as a decimal, this equals what? Just to do it, we can use a calculator here. So in other words,
0.29.
Okay, good. Excellent. Very well done. So we divide 1 by 1530 and we get the answer. And it's 5 out of 17 and we get the decimal, which is 0.29. 0.29. Okay. Then the next thing. The next thing. Right. So now we're going to continue to then say, because it's the probability of female skydiver and having broken a limb. So we did female and broken a limb. And then Now we are actually going to proceed and then check this to then say, if we do the probability of female times the probability of broken limb, female and broken limb, what is the probability of female alone? What do you think?
748 over
Well
the
done.
thousand.
It's 748 over 1530. You agree?
Yes, sir.
Multiplied by the probability of broken limb.
913.
913 divided by 1530. Okay. Now, if you can do this in the exam, the distinction is loading. If you can do this, then the level 7 is loading. It's coming. Okay, so yeah, this is exactly how we need to do the probabilities here. So that we have 748 divided by 1530. And we proceed to multiply by 913 divided by 1530. We have the answer. It is 0,29. 0,29. Like so. We excited. But what are we able to see? It is that this probability of female and broken limb is 0,29. The probability of female times the probability of broken limb is also actually 0,29. They advance. This is the conclusion. They advance. They advance of female and having broken, right, a limb are independent. This is the conclusion. Are independent. Any question?
No.
No question. We move forward. We move forward. Let
Yes,
us
sir.
deal with the shirts. There are 7 different shirts, 4 different pairs of trousers. So we have 7 different shirts, 4 different pairs of trousers in a cupboard. So you have your shirts at home, and you also have your pair of trousers in a cupboard. The clothes have to be hung on the rail. You need to hang them on the rail. In how many different ways can the clothes be arranged on the rail? We're good. Right,
Yes.
so this one is a very easy one. Right. Okay, so this one is a very easy one. Let's indulge and enjoy ourselves. Right, so if we're dealing with the shirts, what do we do with these shirts? These shirts are very, very awesome, and we're excited to have the shirts. Right. Okay, so now we want to participate here a little bit because I need to get your mind working. We did an example like this. And then now I'm just giving you this one as a little test because I must give a follow-up exercise. But you see, not something very much the same, but slightly twisted. The question is, in how many different ways can the clothes be arranged on the rail? We want to arrange all of them. We want to arrange all of them. So now if we arrange all of them, what do we do here? Dear, your take.
Um, I, I wanted to. There's two things that I'm thinking,
Yes.
right?
What do you think?
It's either we we add. 7 plus 4 and then factorial it, or we factorial the 7 and then factorial the 4 and then add
Okay,
them together.
excellent stuff. I'm excited that you're thinking. Those are the students we want. We want students who think, and you think, you reason. And this is it, because these are different. These are what? Are different, because if they're different, then we have the 7 and the 4, and we factorial them like this. So well done. And if you do, we have 7 and 4, they give us exactly 11, and we factorial the 11. And if you do factorial the 11, you get the answer as follows.
Hold on.
What you got?
Wait, I had the answer. It's 3991680.
3991680. Right, so that is correct. So you're getting 39916 800,
So
like so.
can I
Yes, please.
can I ask
Yes.
when do I factorial the two events, the two numbers differently and then add them?
Okay, that's a
In
good
which case?
question. Under what conditions would you factorial them separately? Right. So you would factorial them separately when you have to either do um, this one or that one. It's when you have to actually do arrange the shirts or the trousers. So
Okay.
you would now, or if they would say or, then this translates to addition. Or translates to addition. But and translates to multiplication. Anyhow, we are really adding these things here. But in principle, what you are having is that all these things are different. So you are dealing with 11 objects. That's what is happening here. You are dealing with 11 objects. And the first object can be put, so you are doing this, like we're doing.
Oh, okay, okay.
You are doing this like you're doing. You are just putting the 74 here. We're doing this so that it is and therefore we are multiplying everything here. So the first one is 11 ways. The second one is 10 ways. Because you put the first shirt and then if you have 11 objects, then you are left with, if you put the first shirt, then you are left with how many shirts? 6 shirts and like 10 things, 10 objects. After we have put the 10 on the rail, then you're left with 9. You have 9 choices. After that, you have 8 choices. After that, you have 7 choices. And so on until you have only one choice, one item left to put on the rail. So that in the end, then it becomes factorial, 11 factorial because of that. Then why do we just say 7 plus 4? Well, we understand that what we're doing, we're dealing with the total of 11 different things. So if 11 different things in principle, we need to add them up. But also, even if you have 11 same things, what about if you have 11 same things? 11 identical things, you would still add them up. So in all cases, dealing with arrangements would just be adding them up. And then, if there are similar things, you add them up and you divide by the number of the things that are common, like we did with,
Okay.
then if there are similar things, you divide by the number of the things that are common. But yeah, it doesn't apply in this question. Okay, we'll move on to 6.2. Right. In how many different ways can the clothes be arranged if all the shirts are to be hung next to each other and the pairs of trousers are to be hung next to each other? We're looking at 6.2. In how many different ways can the clothes be arranged if all the shirts are to be hung next to each other? So we are saying the shirts, we put the shirts next to each other and the pairs of trousers next to each other. We put the trousers together and the shirts together. So in how many different ways can this be done?
Mm,
Okay. All right. So you think you reason. So if we put the shirts together, so we have 7 different shades. 7 different shades, but also have 4 different pairs. So now what then is all this here? What this translates to is the following. So you're going to say the number of ways, 6.2. Number of ways. Right, 7 different shirts would become what? So because they are 7 and they are different, you're going to do them like that. 7 of them. So you're going to have 7, 6, 5, 4, 3, 2, 1. Okay, you can't repeat the shades because each shade, there are 7 different. So you're going to have 7 factorial. Because it is and, you must put all the shades and then to be hung next to each other. And the pairs of trousers. Now, how many trousers are there? 4 different pairs of trousers. So the trousers are what? The trousers are 4. So you're going to do them like this also, the trousers. So you're going to do 4. You're going to put you have 4 choices for the first trouser. 4 choices for the first pair of trousers. 3 choices for the second pair of trousers. 2 choices, and then 1 choice. Okay? And then now, it is either you put the shirts first and then the trousers second, or you put the trousers first and then the shirts after. Because you can decide to start with the shirts. Because now it is end, so you multiply by the trousers. Or you start with the trousers, putting the trousers on the rail, you hang the trousers, and then after that you put the shirts. So now, as a consequence then, your teacher sometimes will tell you that it is 7 factorial, 4 factorial times 2, because you can either do it, you can do it in 2 ways. You can do it in 2 ways. So you start with the trousers and the shirts, or the other one. So it's the same thing. So in this case, therefore, it is 7 times 4 times that. When the order of things now, because there are 2 types of things here. So now you multiply by 2 because you have shirts and trousers. You multiply by 2. Okay. Now, as a consequence, then you have this. Okay. Right. So you take a computer, your calculator. Right. So if you take your calculator, then you're going to have 7 factorial. Right. You're going to have exactly 7 factorial times 4 factorial times 2. Right. It is 241,920. 241,920. Right. So you have exactly 241,920. Any question?
Oh, before I wanted to ask about one thing.
Yes.
You know, with mutually exclusive events,
Yes.
or I'm not sure, or like when they say probability of not something, and they equate it to one. How does that work?
Okay. The probability of not something. Yes. Okay. So remember that the total probability is 1. So now if you say the probability of not something, it is 1 minus maybe the probability of not P, or let's say the probability of not A is 1 minus the probability of A.
Okay.
Okay. So yeah, this works if obviously we're dealing with an event A and we are dealing with the probability of not A. So this is one way of doing that, really saying the probability, in other words, the probability of A plus the probability of not A is 1. In other words, the total probability of A of something or not something is always 1. That gives us sort of the total probability.
Okay.
Right. Why? Why is it this? Because if you look at the event space and we have an event A, so the probability of A and the probability of not A So probability of A is going to be the probability of A in A like this. Then the probability of not A is going to be outside like this. So that the probability
Mm-hmm.
of everything in the universal set, the probability of everything in the universal set is what? Is 1. All right.
Okay.
All right, good. Let's move to the next question. All right, we're gonna go on until 8:15. And then we shall
Okay.
stop at 8:15. Okay, nobody, you need to load a lot of energy when you come to this discussion because we sit here for 2 hours. Right.
Yes.
If you need to take a break, you let us know. Right, let's look at
Okay.
6.3. What is the probability that a pair of trousers will hang at the beginning of the rail and a shirt will hang at the end of a rail? Of the rail. So, what is the probability that a pair of trousers will hang at the beginning of the rail and the shirt will hang at the end of the rail? So, in other words, we are saying, what is the probability that a shirt at the beginning, right, a shirt at the beginning and trousers at the end, and trouser and. So what is the probability that a shirt? There's a shirt at the beginning and trouser at the end. What do you think?
I'm not sure actually. With this one, I'm not sure.
All right, that's fine. 4 marks. 4 marks given there. Right, so there's something you need to take into account here to move on. It shall run up to 8:15. But you need to take into account the fact that if you are to deal with this question and you are dealing with a total of how many objects here, you are dealing with 7 shirts that are different, and you are dealing with also 4 pairs of what? Of trousers. Okay. So what is the probability that the pair of trousers will hang at the beginning of the rail and a shirt at the end of the rail? Okay, we're good. Let's discuss this together. So now you are dealing with a total of 7 plus 4. What is 7 plus 4? 7 plus 4, it's 11. That you know so well. But if we put the 11 things like this, and we are 100% sure that we want to find the probability that a pair of trousers will hang at the beginning. So we put T for trousers. We put T for trousers in the beginning. And after we've put T for trousers in the beginning, we then put the right, look, the probability that a pair of trousers will hang in the beginning of the rail and a shirt at the end. So we put a shirt in the end like this, or shirt at the end like this. So now it means that out of the 11, we say 11 minus 2. What is 11 minus 2? It's exactly 9. We're going to deal with 9 objects to organize. 9. We're going to have 9 choices. The rest of the things, we shall put them in the middle. So we're going to have 9 choices here, and then 8 choices here, and so on, until you are left with 1 choice. But in the end, we actually would have the following. You would have exactly 9 factorial possible arrangements times. So now, after having organized the right, because we want to find a probability that a pair of trousers will hang at the beginning, put a pair of trousers in the beginning, and a shirt at the end, right? And obviously, we have 9 things to organize, 9 items to organize on the rail. We have 9 choices until 1. And then right now, we continue to then say, after that, what then is left for us to take into account? There are a couple of things that we need to take into account. What are they? Right. In other words, you need to take into account the fact that we were dealing with what? we were dealing with a total of 4 different pairs of trousers, but also 7 different pairs of shirts. And so right now, we're going to organize them in how many ways this? Right, so we're going to organize them in what? We're going to organize them in we can put 4, doesn't matter, 7 or 4. 4 by 7. For the 4 trousers, 7 shirts divided by the total of everything, 11 factorial. 11 factorial.
So can you please repeat that again? Like from the
Yeah,
9 factorial.
yes, from the 9 factorial.
Yes.
So this is what we have here. This is what we have here. There are a couple of things you need to take into account here when you do these arrangements. I want to state categorically that for the trousers, you put a T. And for the shirts, you put an S. And then now, because there must be, according to this question, what is the probability that a pair of trousers will hang at the beginning? You put pair of trousers in the beginning, at the beginning, and the shirt at the end. You agree? Okay, good. Let's get here. So now, if then the trousers are in the beginning, in how many ways do you choose the trouser? How many choices do you have to identify the trouser? Because you must choose from how many trousers this the pair of trousers to put here. You choose from how many? From the 4 that are there. So in other words, for the trousers, you have 4 choices here. For the pair of trousers that is going to put in the beginning. After that, you need to put a shirt in the end, but you choose from how many shirts? There are 7 different shirts. So it means that you'd have 7 choices, 7 shirts to choose from. That is why you have 4 and 7 multiplied by the total arrangements of the things in the middle, the shirts and the trousers that are going to be remaining. And there are 9 of them. And those ones you can do it in 9 factorial ways. So that in the end, then it's 9 factorial times 4 times 7 divided by the total arrangements of everything. We're dealing with the 4 plus 7 factorial for everything, which is exactly what? 11 factorial for what? For everything there. Okay. So that now, what is this probability? All right. So, be good. Dealing with the probability question, we're going to stop at 8:15. I said ready. We sit here for 2 straight hours. If you want to stand up, you let us know. Yeah, but it has not been popular practice. But I mean, if you want to stand up, you want to go to the and drink water, whatever, you let us know, so that because we sit here normally for 2 hours, we just assume that you actually obviously gather the energy to sit here. So that in the end, then the calculator simplifies it to 14 divided by 55, 14 out of 55, which is 0.254. 14 divided by 55, 0.254, approximately. 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 All right. Any question?
Can I recall what I understand and then you'll correct me?
Yes, please.
So basically, what you're saying is that for the 9 factorial, we got it because we minused the 1 trouser and the 1 shirt, and then we
Yes.
worked with the ones in the middle, and there was
Yes.
9. So there's a 9 factorial. And then
Yes.
the 4 and the 7 is the choices in general that we're going to have to choose from.
Yeah, the choices, because now for you to put the pair of trousers, you need to put a pair of trousers in the beginning. but you choose from how many
Four
trousers?
choices.
You have four
Okay.
choices because you choose from four trousers because they're
Okay.
different. So you can either take maybe the blue one, the red one, the brown one, the green one, depending on the colors that are there. But because they are four different, but you need to choose from four. It's not that you'll just take one and put, but you'll have to choose because you can't take all of them. But you have four choices to make. And then
Okay.
here, for the shirts, there are 7 shirts altogether. But you must put only one shirt here at the end. So to put only one shirt at the end, you choose from how many shirts? From 7 shirts. So you have 7 choices to make. You know,
Okay.
and that is why
Makes
you have the
sense.
4 and the 7. And then now the after 11 minus 2, then you remove the 2 that you have put there. Then the remaining things in the middle. Now 11 minus 2 is 9. So you're left with 9 pairs of trousers and shirts that you need to organize, which are non-pictorial, you know?
Okay.
Okay,
Makes
good.
sense.
Right. So we move on to the next question. Okay, now, one thing that is very important for you as we actually are discussing this, and this is our last question, right, on the probability theory for today, it's going to be the tree diagram story, right? The probability that it will rain on a given day is 63%. There's a probability that it rains, and this probability is 63%. It might rain, and the probability or the chance is 63%. A child has a 12% chance of falling in dry weather and is 3 times as likely to fall in wet weather. A tree, now draw a tree diagram to represent all outcomes of the above information, right? So this is it. How do you draw a tree diagram here? So there are 2 possibilities first. It is either there is rain or there is no rain. It is either there is rain or there is no rain. Right, so take note. The probability to rain on a given day is 63%. So in case it rains, the probability is exactly 63%. Right, we're good. We continue. Maybe I can put it somewhere here to create a bit more space. So you have this and you have that. So now you then say, it is either there is rain or there is no rain. 63%. Now, a child has a 12% chance of falling in dry weather. Okay, let us look at this. 12% chance of falling in dry weather, and is 3 times as likely to fall in wet weather. Okay, right, let's look at this tree diagram now. So now there are 2 possible outcomes here because either the child falls, the child happens to fall, or does not fall. In the same way that if there's no rain, we understand that the child might fall or the child might not fall. Okay, the child might not fall. So now, if the child falls here, what is happening here is that there is rain and also the child happens to fall. There is rain and the child falls. Here, there is what? Here there is rain and the child does not fall. Okay, here there is no rain and the child falls. So no rain and the child falls. Here there is no rain Right, here there is no rain and the child does not fall. Does not fall. Right. No rain, the child does not fall. Okay, we're good. Let us just complete this up quite quickly. All right, so now if the probability that a child has a 12% chance of falling in dry weather. Right, so now we agree that it is 12% chance in dry weather. So what does it mean? It means that whenever there is no rain, we understand that potentially there is dry weather, and therefore there is a 12% chance of the child falling. Okay, if then the child falls and there's a 12% chance of them falling, and then not falling is 88% because it's 100 minus 12. 100% minus 12. Now, 63% is the chance of rain, and then there is 100% minus 63, which is 37%. 37% of no rain. Now, there is the chance of a child falling. Now, here, they're saying, and is 3 times. 12% chance of falling in dry weather, and is what? Is 3 times as likely to fall in wet weather. Okay, so obviously when it's wet, the child is likely to fall more, but is 3 times. So it is 3 times 12%. And 3 times
36.
12% is 36%. So in other words, if it's wet, the child has a 36% chance of falling there. Okay, so now it's wet and there's rain, so the chance is 36% of falling. Right, and then 36% minus 100 is 64% there. All right, good. So now we have our tree diagram, and our tree diagram is complete. Draw a tree diagram to represent all outcomes, and all the outcomes are there. Any question on this tree diagram?
No.
No question. Let's look at
Yes.
3.2. What is the probability that a child will not fall on any given day? Right. On any given day, we're saying, hey, the kids are strong and they do not fall. In other words, we are saying the probability of the fact that the child does not fall on any given day. Let us check these together. So what do you think that probability is going to be from the tree diagram? Does not fall.
Does not fall. Is it
Yes.
not going to be 84 plus 88? I mean, and 64. I don't know.
Okay, yes, yes. Because now you can see we have not fall here and not fall there. We have not fall here and not fall there. Right. So if you have not fall at the bottom, for instance, not fall here. So now if you look at not fall here, it's gonna be first 63 over 100. So not fall at the top is 63 over 100, followed by 64 over 100, like that. Or not for this one, not for this one. So in other words, it's going to be 37%, 88%, not full. Right, so we say the probability of not full. Right, so we're good. Let's do this. The probability of not full. Okay, right. I know that we have gone beyond the quarter past. We're rounding up, please. Right, so now let us do this quickly. So what is this? This is 63 over 100 times 64 over 100. Right, and that is exactly 252 over 65. It's exactly 252 over 625. Plus, doing this one is 407 over 1250. And if you use a calculator, you get 911 out of 1250. And this is approximately
17.
0.7288. 0.7288. Any question?
No.
Okay, good. Now let us look at the next point. So we're looking at 3.3 right now. And 3.3 says, what is the probability that the child will fall in dry weather? The probability of dry and fall. The probability of dry and fall.
37 over 100 times 88 over 100.
All right, well done. So the probability of dry and fall. So you are able to see that at this point, if it's dry there, the rain and fall would be actually 12%. So now the probability of fall in dry weather, that is going to be exactly 37. 37 over 100. Right, so you're going to have exactly 37 over 100, and this is multiplied by 12 over 100. And if you use a calculator, you get 1111 divided by 2500, and the answer is 0.0444, like this. So the probability that a child will fall in dry weather is 0.0444. Any question?
No.
No question. We proceed to
Yes.
the next one. Right. So now this is your homework. This is your homework. You don't need to copy it down because it is. We're gonna send you the recording in the next couple of minutes at the end of our discussion. After nearly 30 minutes, we're gonna send you the recording, and you can watch this recording during the course of the week whenever you have a chance to. Okay. Right. But it's a 2-hour recording, and therefore you'd have obviously ample time to watch. But question 11 is your home activity, but it's not very long. Right, a survey concerning their holiday preferences was done with 180 staff members. The options they could choose from were to go to the coast, visit a game park, stay at home. The results were recorded in the table below. Male, female total. We did something like this. The coast 46, 52, 98. The game park 24, 38, 62. Home 13, 7, 20. And you can see the 13 plus 7 is 20, etc. These things must add to that. And now determine the probability that the randomly selected staff member is male. And then number 2 is does not prefer visiting a game park. Does not prefer visiting a game park. This is your home activity. You're going to do it during your own leisure. We can always chat about these next time. So, yeah, right. I understand that our next lesson is tomorrow. Is it correct?
Yes, sir.
All right. Thanks so much for joining us. It was awesome having this discussion. Until tomorrow, take care and good evening to
Yes,
you.
sir.
Okay.
Thank
Thank
you,
you.
sir.
Bye.
Bye.
Goodbye. Do we do finance tomorrow? Do we do finance tomorrow?